I went to the.
So our next speaker is Stephen Morris. Stephen Morris is the J. Tuzo Wilson Professor of Geophysics at the University of Toronto. His research involves experiments on emergent patterns in fluids, granular media, ice formations, and fracture. He is also interested in natural patterns and in the history of physics. He has sometimes passed off his scientific images as art. He is also interested in patterns in nature and in the history of physics. He's appeared occasionally on the Discovery Channel. Stephen earned a Bachelor of Science and a Master of Science from the University of British Columbia and a PhD from the University of Toronto. He was an NSERC postdoctoral fellow at UC Santa Barbara from 1991 to 1993. And in 2003, he won the AP-US SAC Teaching Award at the University of Toronto. And in 2004, he was given the U of T Faculty of Arts and Science Teaching Award. Stephen was a senior visiting fellow at the Isaac Newton Institute for Mathematics at Cambridge University in 2005, and a visiting fellow at Clare Hall at Cambridge in 2006. He became a fellow of the American Physical Society in 2012, and in 2014 became the J. Tuzo Wilson Professor of Geophysics at the U of T. So please welcome Stephen Morris.
Thank you. This is a little weird, okay? This is only the second time in my life I've ever been in this building, and the previous time was about 25 years ago. So this is interesting. So I love this collision of cultures. It's really kind of interesting. I'm going to talk about emergent rhythms in time and space. So I guess the key difference is between this and all the music stuff we've been hearing in the symposium. I'm going to include spatial patterns. In fact, mostly spatial patterns in my my definition of rhythmic patterns. And I want to explain to you about what emergent means. Here's a kind of easy example to look at. You see, you go to the beach and you see, this very random turbulent wave action on the sand. It tosses the sand all over the place. You might think that such a complex turbulent environment would just produce random arrangements of sand, but miraculously out of this interaction of the waves and the sand, these very, very rhythmic, but crucially not perfectly periodic patterns emerge. So these little defects here tell you that it's a natural pattern. So it's uncannily ordered, but not perfectly mathematically ordered. And so this type of pattern, which is not obviously inherent in the constituents and is not templated from something outside, is what I mean by an emergent pattern. So the big question in physics is, where does structure come from in the universe? We know we can reductively tear apart matter all the way down to what's called the standard model of particle physics. We can reduce everything to 4 fundamental forces and a little catalog of particles that fit on a t-shirt. But the really hard thing is to go the other way, which is to figure out how those ridiculously simple rules somehow conspire to produce larger and larger and more complex things. And you might think that if I took a whole bunch of gas and I just sort of threw it into space, that it would glom together and produce some kind of random looking arrangement of gas. But what you find instead are these, in the universe, you find these very regular looking, striking to the eye structures like spiral galaxies. Why the heck would the stars organize themselves into this remarkable spiral pattern? And the first answer, one answer, is that if I start out with a uniform arrangement of gas, it's unstable. The reason it's unstable is any tiny density fluctuation in there gravitationally attracts the matter around it, and it tends to fall together. Okay, so the structures I'm going to show you, almost all of them have the characteristic that they emerge from an instability, an unstable situation. And it's the outworking of that instability that organizes the structure. Okay, so we call such structures coherent structures. So here's a musical example of a coherent structure. We could actually even demonstrate this, I suppose. The structures I'm talking about are the result of runaway feedback loops, and the situation that at least at the beginning is completely unstable. So here's the unstable situation. We take a guitar, we connect it to the amplifier, we turn the amplifier to 11, and then we do what you do. You turn your guitar toward the amplifier. And you might think that if the room was very quiet, nothing would happen, right? But you all know that that's not what happens. What happens is the tiniest little rumble, the little noise that amplifiers make when they're turned to 11, a little tiny rumble, will run around the loop and get louder and louder and louder and louder, right? But of course, it can't get infinitely loud. It eventually runs up against the top of the volume of the amplifier. Now, if it's a good amplifier, it's linear, okay? That means that the input is proportional to the output exactly. But this problem can never stay linear because it will always run around until it bumps into the nonlinearity of the amplifier, okay? So an inherent feature of these runaway feedback loops is instability, this kind of feedback, but also nonlinearity. And that means that eventually the instability becomes large, and then it runs into the inherent nonlinearity of the system somehow. And it's the nonlinearity that stops it from becoming infinitely loud, okay? And when it reaches that state, we call that saturation. So that means that inherently all these structures have the property that they're unstable. This instability does not remain small. It grows until it gets as big as it possibly can, and then all the complex nonlinearities of the problem are order 1, as we say. They're all there. And they have to be that way because if you didn't reach the nonlinearity, it would just keep growing, right? Okay, so that's the characteristic of all of these systems. Now, what's miraculous is if you turn your guitar toward the amplifier, you might think, well, there's nothing. I'm not playing any note. What's determining the sound of the scream? Well, the answer is that it's some kind of, it's the inherent feedback that's selecting the note. That whatever comes out of the amplifier goes into the guitar and goes around to, so somehow the structure of that sound comes from this highly nonlinear outworking of the instability. Okay, so another little subtlety of this is that these systems can never be completely in equilibrium because they require a constant energy input. The amplifier and the whole system has some kind of friction in it, has dissipation. So that means you must drive this thing constantly with external energy to keep it going. As soon as you remove the power from the amplifier, the whole thing will stop working. So that's a characteristic of all these problems, is that they're non-equilibrium driven and have dissipation or some kind of friction going on in them. So here's a little puzzle for you. You can see these kind of things like a meandering river. So this is a structure. It has a characteristic wavelength, but the amplitude of this wavelength is not small. In fact, it gets very, very large. And not just mean it's large compared to the size of the river. It'll actually pinch off if you let it continue. This bow will hit that bow and they'll pinch off. And you might say, well, this is sort of strange because you'd think that if Mother Nature were somehow optimal, if she didn't waste anything, if she was concerned with getting the water to the bottom of the hill most efficiently, why would she allow this crazy thing of this meandering river to occur? And so there's this idea that nature is somehow economical and that therefore would optimize something. But what I would like to argue is that that's a wrong idea. The nature we're talking about is not in equilibrium, not optimized. It's falling down the hill all the time, right? And it's stability that matters and not optimality. Nature doesn't care how fast the water gets to the bottom of the hill. What matters is that all the nonlinearities of the problem are allowed to be amplified as far as they can go, okay? So the reason the river is not straight physically is quite simple. If I were to dig a straight river here and let it flow for a while, the tiniest little undulation in the shape of the river would be amplified by the flow. It turns out that every time a river bends just a tiny bit, it gives rise to what's called a secondary flow, which is a flow transverse to the main flow of the river. And that secondary flow is in the direction to dig away the outer bank and dump the sand on the inner bank. So a straight river is unstable. The slightest pebble out of place will give rise to a flow which will make that pebble, push that pebble on the other side of the river, and eventually the river will become meandering and the meanders will get bigger and bigger. And nothing stops those meanders except that they eventually pinch off. Nature doesn't care how fast the water gets down to the bottom, right? It's not optimality, it's stability or lack of stability that matters. Okay, so here's another kind of coherent structure. If you look in biology, of course, you can find many, many coherent structures. And one of the sort of dogmas of biology these days is, oh, it's all in the genes. The genes will program the body, and the genes are optimized by evolution. Well, bollocks. In fact, your genes do not contain nearly enough information to be a blueprint for the body, right? Somewhere in your genes, you might think there's a number 5. It says how many fingers I'm going to have. Wrong. The genes, the DNA contains no information about that. How does your skin know where to put the hairs? On my arm is very hairy. There, you might think, well, somewhere in the DNA there has to be a coordinate for each hair. Okay, that's just wrong. Okay, the genome is not a blueprint for the body. It's a recipe for the body. Okay, and it's the outworking of the simple rules of the recipe against all the growth and nonlinearity and all that stuff that gives rise to the body. So the hairs, for example, all that's programmed is that each cell will consult its neighbors, and if the nearest hair cell is too far away, then the genes to become a hair cell are turned on. That's all. And in that algorithm, the hair cells grow with some density on your arm, and they're not too close to each other. But their position is not determined by anything except the random fluctuations of where the first hair cell starts and the next nearest hair cell is, right? So it's the process of growth against the nonlinear growth processes that gives rise to the form. It's not the blueprint. Okay? In fact, there's only a tiny bit of information in the DNA. There's only a few, 100 megabytes of information. It's nowhere near enough to determine the full shape. So you might say, well, here I have this amazing shell. It has this amazing spiral. It must know math. The spiral must be programmed in there. And so some kind of benevolent being must have imposed some mathematical regularity on this thing. Nonsense, okay? All the nautilus knows is to grow. And as it grows, it becomes uncomfortable. And when it becomes uncomfortable in the shell that it's got, it simply moves itself a little bit out and grows a bit more shell. That's all there is to it. And from that process, a logarithmic geometric spiral just emerges, okay? So the key thing about emergence is that its structure, which is not obvious in the program of the thing, but emerges from the outworking of those simple rules. So you can make simple rules, simple physics if you like, and in that physics you can't see any structure coming, but that structure will just emerge from those simple rules as a result of a process. And that process is typically one of these runaway nonlinear processes with saturation. Okay, so if somebody ever asks you, does the nautilus know math? Why is it this beautiful form? Well, the answer is that beautiful form is just the simple solution of a simple process that the creature has to go through. And it's very conservative. All it does is keep the shell that it's already got and make it a little bigger to accommodate itself. It moves into the next chamber, actually. So the living nautilus lives in the last chamber, and whenever it feels uncomfortable, it shoves it a little bit forward and makes a new back and grows a bit more shell, and that's all there is to it. And if the nautilus grows linearly in time, then this type of spiral emerges automatically from that process. The nautilus does not need to know, and is in some sense not aware of the beautiful shell that it's made. Okay, does that make sense? So what I'm going to show you is a kind of collection of systems that we have studied in my lab, and with an eye to understanding the emergent properties of them. And all of them have the property that they are rhythmic in some way, some of them in time and some of them in space, and some of them in space and time. Okay? So the result of these kinds of processes is oscillations, waves, stripes, ripples, spots, spirals are also possible. So here's the sand. This is actually a dry version of the sand dune. The wind blows over a dry sand dune, and it's some kind of interaction between the wind and the sand. It's not just the sand itself or just the wind, which pulls out a wavelength of this, almost perfect wavelength of this pattern, but with defects. And that wavelength is nowhere obvious in the initial problem. I could give you all the sand you want, and you could examine it microscopically, and I could tell you all you need to know about the flow of the air, and you still would not be able to see, not be able to predict exactly how the interaction of the wind and the sand ripples amplifies the ripples and produces that wavelength, which is about this big. So nowhere in the problem is that wavelength clear. It is emergent. It is an emergent property of the interaction of the sand and the wind. It's not in the wind or in the sand. Okay, so the first system may be surprising. It's icicles. I am known as Dr. Freeze for my long obsession with icicles. I have been studying the morphology of icicles for more than 10 years, not full time, but for a long time. It's like saying I've been working on my house for 10 years. It's true, but I don't work on it every day. But I've been worked on various versions of this experiment for about 10 years. And one of the features of icicles, which is very fascinating, is the fact that natural icicles are often rippled in their structure. So these are actually 3 natural icicles. This is on the side of my house, and this one's on my top deck. And this one I pulled off the internet, but I got permission to use it from the guy because it's such a beautiful picture. And what you'll notice is that the icicle, if you start an icicle, it doesn't just remain a carrot shape, it has this kind of bumpy pattern to it, or at least some do. And this is a pattern and I'll show you it's both a pattern in space and in time. So how do you study icicles? Well, you could study natural icicles. You could, put your boots on and go out and collect them, but they're uncontrolled. You don't know the history of their formation. So we built a machine, and it is about the size of a beer fridge. It's a refrigerator, a homebrew refrigerator. Water is dripped in the top onto a little piece of dowel here, and as the water drips off, the surrounding air is considerably below zero, and it freezes, and what water that drips off the end of the forming icicle falls into a funnel, and the funnel is kept a little bit warm so it doesn't get too icy, and it leaves the experiment. So we grow an icicle inside of this controlled environment. And then we actually rotate the point of support very slowly. And the reason for that, so it takes about 8 or 10 hours to grow an icicle. So it's a very slow process in real time. So what you're seeing in this movie is actually a speeded up version of the experiment where each second is worth 10 minutes of real time. And we rotate the icicle for 3 or 4 different reasons. One reason, it's just so cool to have rotating icicles. Who would have thought such a thing? The second reason is that for the same reason as you rotate your meat in your barbecue while you're cooking it, you want all sides of the icicle to be equally treated, and the simplest way to do that is just to rotate it slowly compared to the way the water flows on it, but quickly compared to the time it takes to grow. So we rotate the icicle about once every 5 minutes or so. The second reason is that we wish to know the shape of the icicle, and a computer is very good at picking out the edges of the icicle in a picture, so the transition between the edge and the black background, but it can't really measure anything else. So by rotating the icicle and knowing what its rotational position is at all times, we can make a 3D scan of the icicle's shape. So we in fact know the full 3-dimensional shape of every icicle at every moment. Another subtle reason is if you want water to run over all the surfaces uniformly, it's better to put the nozzle, the dripper nozzle, a little off center and rotate than to put it in the center. Okay? So for all these reasons, we rotate the icicle slowly. It looks like it's tearing around, okay, but if you watch this in real time, you would not even be able to see it move because it's rotating once every 5 minutes. Now what you'll notice about this icicle, which is made with distilled water, is that it's a rather beautiful, symmetric sort of spike shape. And there's actually a whole mathematical theory, which I will spare you, about the ideal shape of an icicle, and it does actually resemble the experimental icicle shape. But what you will notice about this icicle, which is made of distilled water, is that what? It does not have any ripples, okay? So like everybody, we started the experiment by putting tap water in the machine, because that was just simpler. And now I'm showing you a movie where I show you each rotational position of the icicle animated separately. So this is the same icicle growing 8 times from 8 different rotational positions, but it actually is rotating slowly. You'll notice that this icicle is pretty close to the same overall shape as the previous one, but it has ripples. Now I have to break it to you that the only difference between this icicle and the previous one is that this is made with Toronto tap water and the other one was made with distilled water. Okay, this is a clue. So what do we know? The ripples are sort of Michelin Man-like in their formation. They're not really sinusoidal. They're a little bit cuspy, so the bottoms are a little pointier than the tops. And the other thing which is quite mysterious is if you measure the spacing of the ripples on a natural icicle or a laboratory icicle, you find the spacing is always very close to 1 centimeter in scale. And that means if you're out in the woods and you drop your meter stick, you can always break off the nearest icicle and it makes a pretty good meter stick. We have never observed an icicle which had a wavelength which was significantly different than 1 centimeter. That's just a fact. And as I was just saying, ripples are not observed on distilled water icicles, but they are observed on slightly dirty water icicles, so they must have something to do with the water purity. So here's the crucial experiment. Whoops, I gotta go back here. So here's 3 icicles. One is pure water, distilled water. One is a tiny little bit of salt, just enough sodium chloride to give it the same dirtiness as Toronto tap water. And that turns out to be about 1 part in 10 to the 4 by weight. So it's a very tiny amount of salt, a few milligrams per liter. And the last one is a bit more, like about 100 times more. But it's still nowhere near seawater. Seawater is several hundred times more than this one. And what you'll notice is that this one has ripples, but it's basically the same shape overall as that one. But as you add more salt, the overall shape starts to suffer, if you like, and the ripples get larger and the whole thing gets more blobby in shape. Okay, so how do we actually measure something? This is physics, right? We need to measure something. So what we do is as I was telling you, is we train the computer to look in the picture and pick out the edge. So this is if I take on the right-hand edge and I animate that line as the right-hand edge as the icicle is growing, and I color code the amplitude of that ripple in this color plot here, like a topography plot, then you can see the ripples appear, these little patches, these little stripes are the ripples at a wavelength of about a centimeter, and they appear in these little patches. So the final amplitude of the ripples is a few millimeters. They're a few millimeters high. Okay, so now one more. Now we can measure everything, and I won't bore you with all the data. We can measure how fast they grow as a function of temperature and flow rate and salinity and blah, 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 lots of things. But one of the weirder things is the following observation. If I take a icicle with a small concentration of salt, and if you focus your eye on the ripples, which are they moving or are they stationary? They grow out, yeah, but where do they go? Up or down? Up. Okay, so it turns out that the icicle ripples climb the icicle very slowly as the ice grows for low salt concentrations. If I do the same experiment for a large salinity, it's blobbier, okay? But if you focus on a peak of a ripple, you see that it moves downward. So the ripples descend for large concentrations of salt. And here's what the data looks like. This is the salinity over 4 orders of magnitude, in other words, a factor of 10,000. And this is rather low salinity. And you see they have a positive velocity. That means upward in this model, in this picture. And the ones that have a high salinity move down. And this is kind of funny because there's actually 2 theories of icicle ripples. Neither of them accounts for the salinity at all. And one theorist believes that they should move up, and the other believes that they should move down. Okay? So 2 theories, 2 possible signs, 2 theorists. It all works out beautifully, right? They're both wrong. And in fact, it goes up sometimes and down the other. And so if you pick a magic, Goldilocks salinity in the center here, they move neither up nor down, like the good old Prince Duke of York, right? This is an interesting observation, and we have many other interesting observations, which I will spare you. So what are the burning questions? I never get to use that. The burning questions in icicle physics: why are the ripples always at 1 centimeter in wavelength and not some other wavelength? It's like the ripples on the sand. That wavelength is not obvious in the problem. We can't pull it out by looking, something else is a centimeter. There's no template that's telling the icicle to have ripples 1 centimeter. Why are they 1 centimeter? Why do I need salt at all? Or impurities at all? If I take the impurities out, the ripples go away, put them in, they come back. And we've tried different impurities. So far as we know, all impurities have this effect. And why do they go up and down, depending on the concentration? Well, there's a real simple answer to all these questions. We don't know. And it's a remarkable fact that the theory, which, by the way, is a very elaborate theory, Jun knows what I mean. It involves fluid mechanics and thermodynamics and solving a lot of differential equations. And at the end of the day, it blows up and fails to explain anything. So, the moral of the story is that you can learn a lot by doing an experiment, but you can't learn the explanation really without doing the theory, and the theory is much harder in this case. We don't have a theory. So this is an outstanding problem. And I have a PhD student working on this problem right now. So we have all this data. We did something kind of fun with it. I took all of the measured icicles and I put them together in something called the Icicle Atlas. And if you Google Icicle Atlas, you'll find each run of the icicle machine has a little home page, and you can download all the images, all the time-lapse movies, all the flow charts and everything. There are about 230,000 images of icicles in the Icicle Atlas, over 400 movies, and it's all absolutely free. I convinced the University of Toronto Library to give it a Creative Commons 4.0 license, and it will soon be hosted by the UT Library, and it's an open data project for the library. So here's a little sample. We call this the Icicle Rogues Gallery. You can click on any of these icicles and it'll take you to the home page, so you can kind of shop for which icicle you like. We can also 3D print large numbers of icicles, and there's lots of fun stuff we can do. So one of the fun things that I got involved with last year was a musical problem, a musical project I got involved with a group called Continuum Contemporary Music. I don't know if people know them here. Last year they put on an event called Collide, and in that event they played a number of different pieces, but one of the pieces was a commission by Jimmie Le Blanc, who he and I collaborated on turning the Icicle data into music, and I'll show you. I can't explain his whole process, but I'll show you a few slides that he gave me. And Continuum played this at this event last year, about a year and a half ago. Here's Jimmie Le Blanc, and here's Continuum practicing this very difficult piece of music. And here's the piece of Icicle, one of the little sample of the Icicle ripple data, which I extracted from a particular Icicle, and I smoothed it a little bit to get some of the noise out. And then I exported it from my Python code, which I used to analyze the data, into a form which can be drawn into his software, which is called MaxMSP, which I'm sure you're all familiar with. I don't know anything about it. But anyway, we made this interface between Python and MaxMSP, and he took it away. And I can tell you precisely that it is run 10823. You can look up everything you want to know about that particular Icicle. And he imported it, and then he used a composition technique to turn that wave that I just showed you. In fact, the wave as a function of the growth of the Icicle, he turned that into a score of music. And so here is a sonogram showing the increasing complexity of the spectrum of the thing as a function of time. This is actually the Icicle getting longer and getting larger ripples and more ripples. So it's kind of simple. Here the Icicle is kind of short, and here the Icicle is kind of long, and it has large ripples on it, and it slowly grows. And he took that and imported it into his software and turned it into some kind of musical score. And then he used some kind of filtering and transposition, whatever that means, okay? Some process, which I'm not privy to. And then he used additive synthesis to generate sound from that. And this is what it sounds like. And basically what you're hearing is the Icicle growing, and the kind of timbre of it is the complexity of the ripple pattern on that Icicle. And as the thing continues, it steps through more and more complex Icicles, and the sound gets more and more complex. And then, let me just do this. Okay, and then we collaborated also with a video artist named Farina Chandra, and there was also a tape track involving the crackling sounds of ice on a lake, and there's a bunch of more complexity to it. But anyway, in the end, it all was put on at this event by Continuum, and I have a short video of what it sounded like live. And you see that it fades through the video that Farina made. The video is projected at the back of the theater. Okay, I'll stop there. Imagine yourself being me, sitting in the audience, watching these incredibly skilled musicians try to play the data from your experiment. This is a unique experience, okay? All right, so I want to change gears now and talk about a completely different type of pattern, which is a buckling or a wrinkling pattern. If you look at the edge of certain leaves, you see that they don't remain flat. They actually have this kind of frilly nature. That's basically because the edge of the leaf grows too fast to be accommodated, and it'll actually bend out of the plane and become elastic like that in order to accommodate that. And that instability actually is called buckling. And an extreme example are these kind of pink things that people plant in their gardens around this time of year. And they're really, really frilly. They're actually kind of fractally frilly if you want to look at them closely. But basically the plant uses a differential growth to produce a frilly sort of leaf. And you also see a buckling pattern in fluid sometimes. So if you ever make a cake and you pour your cake mix into a pan, you'll see that it goes back and forth in this kind of folding pattern. This is actually lava. We're doing that. So as the lava runs down, it has to decelerate when it hits the pile, and it can't be accommodated by the pile fast enough, so it flops back and forth and produces a kind of buckling back and forth pattern. The classic fluid buckling instability is like if you take honey and you pour it onto your pancake. If you hold the spoon high enough, you'll see that it makes what's called the rope coiling instability. This is actually slow motion. It's a little jerky, actually. But what happens is that instead of just flowing uniformly, axially, symmetrically, it rolls around in a kind of rope, like a rope going down on a deck. This is actually a Newtonian fluid effect for those experts in the audience. There's nothing weird about the fluid here. It's just forced to decelerate so fast, and it's too viscous to squish up, so it flops over and becomes a kind of rope coiling. So what we did was an interesting version of this experiment called the fluid mechanical sewing machine. And there, instead of just dumping it onto a pancake, you dump it onto a pancake which is translating uniformly in space. And so it's a belt. So there's two pulleys. There's a belt, and there's a scraper which takes the honey off the end over here. We actually use silicon oil, but like honey. So it comes out of the nozzle, it drops onto the belt, and it moves along. It makes some kind of pattern on the belt, and then it gets scraped off, and then the belt comes back around clean without any honey on it. And it's called the fluid mechanical sewing machine, and you'll see why momentarily. So here's a little movie that I have, which is accompanied by some surf music. I happen to be a fan of surf music. The band is called the Aqua Velvets, for those of you. So now the belt is moving quickly, and the fluid and the syrup is being pulled out. During the experiment, I will slowly lower the belt speed. As the belt speed goes through a certain value, the fluid begins to meander. And the meander gets larger and larger as the belt slows down. And the music dramatically illustrates this. It's called moody meandering syrup. Okay, so when the syrup meanders and becomes particularly large, something new happens. Wait for it. Okay, so now you see why it's called the sewing machine. So this is called alternate side looping. It loops first on one side and then on the other. And then as the belt continues to slow down, the loops become closer together. And eventually, a third state emerges. Wait for it. There. Now it's looping only on one side. And if you bring the belt to a complete stop, then you're back at the state where you're in rope coiling again, right? So that's called translated coiling. Okay, that video was featured on the Rachel Maddow show without the music, okay? I don't have copyright to the music, so I got in trouble for using that music. But anyway.
We'll do it live here sometime.
Yeah. The whole thing, by the way, is only a centimeter across, so it's very small. So you need a focused camera to see that. All right, so now let's go back to the data. This is the speed of the belt, and this is the height with which the nozzle is pulled up off the floor. And the weird thing is at very fast belt speed, so up here in the black region, you get straight, it's pulled out like it's straight, so there's nothing. Everywhere you see a blue symbol, that's meandering, this state. And everywhere you see a red symbol, that's translated coiling at low belt speed. And there's a little window, a little bubble of alternate side looping, that little green bubble in there. And as you lift the nozzle higher and higher, something happens around 7 centimeters, and a lot of stuff starts to happen. And a good way to go completely nuts is to try and map what's going on up here, because it's a total zoo of craziness, okay? I will focus on what happens just down in this region here where there are 3 basic states. And one of them is kind of in the middle between the other 2. So this is what meandering looks like if you measure the position of the thread just above the belt. So the belt is moving downward in this picture, and the tip of the thread is flopping back and forth on the belt like this. And it's also moving longitudinally along the belt a little bit. So you see it's curving back and forth. The red dot is the tip, okay? This is measured data. So if I smear that out in time, it looks like this meandering pattern up here. And if you look at the spectrum of it, you see that there's one frequency at 2 hertz, and the other frequency, the y direction frequency, is at exactly twice that. So it's like the harmonic, you would say. They're locked in a 2-to-1 ratio. If I go down to translated coiling, which looks like this, that's equivalent to taking the tip of the thread and drawing a circle on the belt, and then translating that circle along and stretching it out, okay? And that actually tells you right away that the 2 frequencies are locked together. They're 1-to-1. Okay, so the x motion and the y motion are locked in frequency, but with a 90-degree phase shift to produce the circle, if you know your math, okay? The cool one, of course, is the one in between. The alternate side looping one has a very simple spectrum, but a very complicated, this thing is called a Lissajous figure. I don't know if you learned this, but it's basically the plotting of motion in x and y directions against each other. That's called a Lissajous figure. So here, this is what the tip of the thread is doing on the belt as a function of the time, and if I stretch that out, I get this alternate side looping pattern. Okay, so it goes around and it loops around like that. Now what's interesting about this is that it's exactly a 3:2 ratio. The x and y motions are locked in 3:2. So it used to be called the figure 8, but we actually changed the name to the alternate side looping because that's more descriptive. But my graduate students came up with other names for it, the yin-yang state, and the best one was the Toyota state because it looks like the Toyota symbol. Okay, so here's the frequencies measured as a function of the belt speed. So at low belt speed, the two frequencies are locked together, and they're equal to both blue is the x and red is the y. They're locked together 1-to-1, and they're both the same. At high belt speed, this one is exactly half that one. So this is the longitudinal belt speed, and this is the transverse frequency, I should say, and they're locked 1-to-2. So that's exactly twice that one. In between, you have this marvelous spectrum, and this is the alternate side looping regime, and the fundamental, if you like, is split between f and 2/3 f. So it's exactly a perfect fifth. I learned that word, okay? Okay, so where the heck did this come from? Well, the answer is there's an elaborate theory and there's a lot of math behind it, but basically the system at that special value is unstable to a frequency 2 to 3 frequency locked state where the frequency in one direction is 3 and the frequency in the other direction is 2 times some special frequency. So what really happens is that this is a kind of a fundamental frequency and it splits right there between the two different directions, and then they squish back together again into this value here. And these other ones, by the way, are harmonics and subharmonics. So this is 1/3 f, 2/3 f, 3/3 f, 4/3, 5/3, and 6/3 f. So that's the octave up there of this one, right? Okay, so that's an interesting experiment. I have a graduate student working on this now. He's working on the chaotic states. If you lift the nozzle high enough, all hell breaks loose and it produces a kind of random looking motion, and that motion is probably chaotic, and that's very interesting. Okay, the last system I'm going to talk about very briefly is something you may have experienced in rural Ontario somewhere. If you drive down an unpaved road, you'll discover that unpaved roads had a tendency to not remain flat. In fact, it can be shown that a flat granular or gravel surface, a sandy road, usually dry, is unstable to the action of rolling wheels, and it produces what's called washboard road. In Australia, it's called corrugated road. And there's basically 3 places in the world where this has been studied by anybody. One is Canada, one is South Africa, and the other one is Australia. And those are the 3 places that have problems with dry roads. It's really an instability because it turns out this wavelength is not what everybody thinks it is. If you think it's because your tire bounces up because it's on a spring, right? Your tire has a spring on it, gives it a special frequency of bouncing. You might think that bouncing times the speed of the car gives you some wavelength, and that should be the wavelength of the washboard. That's completely wrong. It turns out that the wavelength is much shorter than that. It's a new wavelength, not obvious in the problem. So it's also related to something that's perhaps a bit more fun, which is moguls on a ski hill. You start with a nice groomed smooth run, you let lots of skiers go down it, and magically, spontaneously emerges this horrible, maybe delightful if you like it, pattern of bumps, which is a kind of 2-dimensional washboard called a mogul. And I happen to be in possession of the world's only time-lapse movie of the motion of moguls. I wish I could tell you that I made it myself, but it was made by Dave Barr from a little place called Regis University, and he went on a ski vacation and pointed his camera out the window every morning and took pictures. And so now you can actually take a kind of coarse time-lapse of the moguls, and you can see the shadows of the trees move around and stuff. And you will see how the moguls move as a function of time. Focus your eye on a bump somewhere. It's repeating. There's only about 12 frames. So what do you see? The moguls move up the hill. How could this be? Well, the answer is it's sort of the same as the icicle ripples moving up. The skier scrapes off some snow from the lee side of a downhill side of a ripple of a mogul and tends to leave it on the uphill side of the next mogul. And if on average that's what skiers do, then those moguls will travel uphill even though all the snow moves downhill. Okay? And it's the same with the ice. I forgot to mention on the icicle ripples, the ripples move, but no ice moves. Okay? It just means the new ice forms on the top of the ripple more than on the bottom, and so the ice, gets the ripple moves up, but the water moves down. Okay, so you can even see washboard road on railway tracks, even streetcar tracks. I always show this when I give this talk in the United States. We have a little thing in Canada we call rapid transit. In the business of railway business, it's called roaring rails. And if you ever stand near an intersection on the college car, you can hear this noise as the streetcar accelerates past. It goes roar. And that's actually the vibration of the steel wheels on the steel track. And if you take a picture of that track, you'll see that the wear pattern oscillates on the track with a wavelength of about this much. Okay, so here's the experiment. It's quite simple. We are too lazy to make a car. You know, we're not engineers. So we leave the car standing still. We rotate the road, as the saying goes. And so here's a wheel rolling around the outside of a rotating table. And the table has a bunch of sand poured on it. And after you rotate for a while, the wheel begins bouncing along, and you've made washboard road in the lab. And so here's what it looks like if you start with a very smooth layer of sand. The little white dot is to show you how the wheel is moving. What you see is that it rolls very smoothly for a while. Every so often, then it'll hit some little imperfection, some little divot. And then it'll bounce up and down just a little bit. Boom, boom, boom. But when it comes back around to that place again, like the next car coming down the road, it'll dig that divot a little higher and make the next one a little bigger. And after some hundreds of rotations or so, the whole thing will be totally washboard. And so this is what the final state looks like. And this is going pretty fast. The wheel actually leaves the surface. So when you're ripping down the washboard road at high speed, you're actually in the air a fraction of the time. And the Mythbusters have actually tested this. They've learned that you can actually have a smooth ride if you drive fast enough. And of course, that means you're just flying from ripple top to ripple top, and it's very unsteady. And if you try and steer, it's not good, okay? So don't do that. So here's a space-time picture. So in order to make this more visual, we take the position around the table, and we measure the angle the arm with the wheel on it makes with a little transducer, and we make that a color, and this is the time, and this is actually in table rotations. So after about 50 table rotations, it's just smooth. After 100, there's a little patch of ripples appearing, and after 150, it's basically 100% ripply, and then, you know, after a couple hundred or 300, there's ripples all the way around the table. And the ripples actually, this is a maximum and this is a minimum. The blue is a minimum, red's maximum. You'll notice that they lean to the right. So what does that mean in a space-time image? That means the ripples move, okay? That means they're drifting down in the driving direction. So as you're driving down the washboard road, you're advancing those ripples down the road very slowly, just like the skier, only in the opposite direction, it turns out. Okay, so we eventually trimmed the experiment down to the Zen simplest experiment. It's like the handleless axe with no blade. Have you heard this? So now we have no suspension. I forgot to mention there's no suspension. There's no spring at all. We have no wheel. It's just a paddle. We call it the plow. No wheel, no suspension. All you do is you drag an inclined plow over the surface of the sand at higher and lower speeds. And sure enough, it develops washboard without any wheel or any suspension. And so now this is a movie which is a little hard to interpret because I take a picture each time the table is rotated once. So in this movie, the table will appear to be stationary. But in fact, the table is rotating in this direction, so the road is approaching the plow and going under the plow this way, right? Does that make sense? Okay, now watch what happens. You see the ripples appear, they move quickly at first, and they have a small amplitude, and they're a very short wavelength. The wavelength gets longer, the amplitude gets larger, and they slow down. And then later in the motion, you see these kind of coherent superposition on the ripples, like a little kink that moves around the table in the direction of, so this is the direction of driving. So these are the ripples moving in the direction of driving around the table. Does that make sense? Now maybe somebody would like to compose some music using this data. Okay, so now you can look at all different space-time diagrams under different conditions. Sometimes you get backward traveling ripples. Sometimes you get forward traveling ripples. Sometimes you get kind of chaotic ripples. Sometimes you get these little kinks coherently moving around the table at a different speed than the ripples. So that's what this is, sort of a herringbony looking pattern. It can be quite fine. Okay, so there's quite a lot of phenomenology going on here. Now you're going to say, do we understand this? We do, sort of. There's a whole elaborate theoretical description of this. Is it practical for engineering? Not yet. We don't understand it. At the moment, the engineers still don't appreciate that this is an instability. It's not just the tire going up and down or the road rippling. It's a coupled problem of the road driving the tire, driving the road. It's a feedback situation. And at the moment, tire and engineering, people who engineer suspensions don't think that way. Okay? And the railway engineers don't think that way. So we have not so far even convinced them of our basic paradigm for this problem. So we're nowhere near producing a practical thing. And we're not, frankly, that interested in a practical thing. I'm more interested in these pretty pictures and how the and how this simple system produces all this beautiful emergent complexity. Thanks very much for your attention. Yeah.
What was your inspiration for doing some of these experiments, like the honey experiment? Did somebody else do something similar?
The honey experiment is, I actually sort of inherited that from the guys at Cambridge who did the first version of it. And the original version of it was done by one of the most famous classical physicists of the 20th century, G.I. Taylor, who did some experiments with it way back in the 50s. So it has an enormous literature. There are dozens of very mathematical papers on the rope coiling version of the thing. And that's basically been completely worked out, and you would not believe how complex the resulting thing is. So the fluid sewing machine is a kind of generalization of this classic problem that people have worked on for 50 years. And the guys at Cambridge, when I arrived there for my sabbatical, had just built this machine to do this, the sewing machine version. And I kind of took it up from there. So that one has a history, long before I arrived on the scene. What I usually do is I take experiments which have been done by people who don't normally do experiments, like mathematicians or geologists or somebody, and I take them into the lab and I do them physics-wise, right? And so my version of the sewing machine experiment is much more carefully instrumented and much more, and I can measure everything much more precisely than the original version. So that's really my piece of it. So all that data that I showed you is you know, not easy to get. The icicles, I was inspired by just seeing them and wondering what the ripples were for. And there's actually a theory of the ripples by a guy from Japan, which I read. And so that I can say was inspired partly by the fact that I could easily make them in the laboratory, and there was a theory that people had already made at that point. The washboard road is just something you just see. And you know from your physics sense that it's got something to do with an instability of the road, and then I just built the machine. There have been a few experiments on washboard road by engineers before our experiment, but no physicists had worked on it.
What's the biggest breakthrough that you've either found yourself or you've witnessed within your time of research?
Well, depends on what you mean by big, I guess. The revelation that the ripples on icicles were caused by impurities was completely unexpected. And that just changes everything. And anybody could have observed that before if they'd been careful, but nobody was careful before. What people did before was they just did the simplest thing, use tap water. And it turns out that tap water is extremely close to distilled water. It takes a chemist to tell you the difference between the two. You can't taste it. You can't.
There's minerals.
Yeah, but not much. Thermodynamically, the melting temperature and the viscosity, everything about tap water is the same, to many decimal places compared to distilled water. So you might think, why would that make any difference? But it turns out that even tiny levels of impurities make a little bit of difference. So all previous work on ice morphology has just assumed that tap water is the same as distilled water, but it's not. There's actually a whole community of engineers who work on ice buildup on structures. There's a whole conference every year on the International Workshop on the Atmospheric Ice on Structures. And last year it was in Sweden. And I didn't go, but I sent a poster. So if you wish to calculate the ice buildup on a power line, you must immediately confront the fact that even rainwater is dirty enough to be different than distilled water. And all the structure of the ice formation on a power line or a hailstone or a freezing rain event, all those morphologies are different than you might think they are. So that's actually a kind of a big deal. Yeah. food. Not to my knowledge. Oh, that's not quite true. I was once approached by a guy who wished to make a machine that he was going to put in a kind of candy shop that made colored icicles that he could sell for candy. And the trouble with that idea is that as the ice freezes, it excludes most all of the sugar is excluded by the thing and the coloring too. So it's actually not a very practical way to make, you might think, I'll just put sugar and colored water in and make icicles that are colored and sugary, but that doesn't work actually. So that's about as close to an application as we've ever got. I have 3D printed a lot of them, and you can freely download the 3D printed version. And I put them on this thing called Shapeways, if you know your 3D printing thing. It's open, anybody can make it, and some people have printed them. And yeah.
If you had to make icicles in a zero gravity environment, how would you do it?
Well, they wouldn't be icicle shaped.
There's no way to go about it?
Well, I'm not sure what would happen. It's a bit like a flame. A flame depends crucially on gravity and buoyancy, and this depends crucially on the water running down the outside. So I suspect you'd have a problem because your inlet pipe would sort of clog up, and it'd be hard to do. Everybody asks that question. The only thing that gravity affects is the speed with which the water flows down in the thin film on the outside. There's water running down the outside of the icicle. And I can actually change that speed by changing the flow rate too. So there's a dimensionless, what's called a dimensionless number, which is a ratio of flow rates and gravity and stuff, which is the thing that matters. And I can trade things off in there. So if you doubled gravity on me, I can change a knob on my machine and build the same icicle as I grew before. So gravity alone isn't the thing. It's how the gravity and the viscosity and the thickness and the angle and all these things come into it. And those all play off against each other. Yeah?
The icicles with the double tip.
Yeah, that's a good question. You're going to ask me why.
Yeah.
You do see them in nature sometimes. The difference between the icicle experiment and icicles on your house is that we force all the water that we put in at the top to drip off the same icicle. And if you do it on your house, you would probably get multiple icicles on your house. Another little mystery is if you have, I think I showed the little fans in the box, okay? We actually also control whether we stir the air in the box or not. It turns out if you do the experiment with still air, so you don't stir the air in the box, you try to leave the air as still as possible, then the icicles with about 80% probability will split their tips. Actually, it doesn't split at the tip. It splits part way up. And then there are two tips, and they share the water, and they both grow. Sometimes three tips. We don't know why that is. If you turn the fans on and you make turbulent air in the box, it suppresses this instability of the thing, so it tends about 90% of the time to produce a single tip. And the answer as to why that is the same as the other one. We don't have any idea. It's just an empirical fact. But you do see them split. You do see split icicles on the side of your house sometimes. And another little clue is that the angle between the prong and the main body of the icicle is often 60 degrees, which is the angle of an ice crystal. So you can think of the tip as being a kind of fast-growing crystal which happens to poke out far enough to have its own drips, and then it takes off as a separate tip. But the short answer is we don't really understand the tip splitting, but we know how to make it go away by stirring the air. Yeah?
Yeah, so in some of the earlier slides that you showed with your experiment, I would assume that some impurity in the water causes a wobbling effect.
Well,
it doesn't seem to be amplified over time, which is what I
No.
would expect, and then it comes back and corrects, and maybe overcorrects a little bit, but the variation is still
yeah.
self-correcting.
The thing you have to remember is the icicle is not it's not a uniform material inside. It's a crystal, and in fact, it's a multi-crystal. If you cut an icicle in half and look at the crystal structure, it's many little crystals in random directions. So I think that the fact that it kind of wiggles around sometimes is just because crystals grow a little faster in this direction than that one for a while, and yeah, that's it. There are no two icicles the same, right? it's like the
wavelength.
yes.
But the wavelength is pretty constant.
The wavelength of the ripples, yes.
Yeah, the incidence of
Yes,
the
yes. We've varied everything, the temperature, the flow rate, the salinity, everything. And within a certain amount of uncertainty, they all have the same wavelength.
But so the average grain size is really small. Right?
It's millimeters, we think. So it's not small. It's the tip of the icicle might even be a single crystal.
That's as close to a metallurgy question.
Yeah, it's a polycrystal. People have studied this. We're not crystallographers, so we haven't studied the crystal structure, but it's known that they're not either a single crystal, and they're not small enough to be homogeneous either. So they're in some kind of intermediate state. Yeah.
Maybe in the crystals, but otherwise, have you encountered any fractal action anywhere?
Fractal.
Yeah.
Not really.
Like, no.
The closest thing to a fractal I showed you is the frilly leaves that were on that pink thing. And buckling patterns do produce fractal edges. So here's an experiment you can do. Get a piece of 6 mil poly or thick polyethylene, put a little slice in it, and then tear it like this, like you're ripping open a bag of potting soil or something. And then look at the edge. As you tear it, you stretch the edge of the plastic enormously, and it'll riffle up, and it'll actually get 3 or 4 levels of fractal ripples on there. Sometimes I do that. Sometimes I hand out plastic at this talk and do the ripping. Yeah.
So, based upon what you just said about the forked icicles, you predict that you'd get more of those forming on the outside of your house on a day where there was very little wind?
I guess I would predict that, but you go ahead and test that proposition. I think it has more to do with the fact that we're forcing all the water to go down one icicle. And if in nature there would be some kind of support which wasn't that way, and it'd be a second icicle would form instead. And we've engineered it so that not only is the icicle forced to grow from a single point, but that point is not refrigerated, okay? So that the little dowel is held by little wires, and there's no heat transport from that dowel directly into the refrigerator, only goes through the air. On your house, on the other hand, the metal of your eaves trough is very cold, and a lot of heat can be extracted from the icicle through its root, and it's the rate of heat extraction that determines the rate at which the ice grows. So there are certain differences between having a refrigerated support and an unrefrigerated support.
And with the splitting icicle grid, I didn't quite catch if distilled versus impure, which one is more likely?
It happens for both. The ripples are the thing that goes away, but the splitting doesn't go away with impurities, sadly. Yeah.
I was just looking at the painting of the guy playing the recorder there. I'm wondering is there any relationship between the fluid dynamics in a whistle to the syrup flow, or is it?
No. What's interesting about the syrup flow is that the syrup is extremely viscous, and so that means we're a long way from turbulent flow. So if you know what the Reynolds number is like 0.1. Okay, so it's nowhere near turbulent. All the instability is driven by this buckling effect. And in a whistle, you have turbulent jets and unstable turbulent jets blowing across little reeds or whatever you put it. What do you call the little pointy thing in a whistle? The what? The fipple. I learned a new word. But as I understand it, if you basically blow directly at the fipple, and then it flops back and forth across it like this. So that's a Reynolds number effect. We're nowhere near that kind of fluid mechanics, no, right? Yeah.
Do you know if anyone's conducted experiments in reporting, if this is kind of harkening back to what we heard before you were talking, frogs and other insects that appear to have similar emergent qualities of phase and so forth. Do you know if anyone's ever...
You mean the noise that they make?
Yeah, not necessarily here, but in other more tropical...
I read a paper once about a frog from South America which sits at the bottom of a certain plant which is like an organ pipe, and it tunes its grunting noises to resonate with the organ pipe because it's louder, right? I mean, you know, the frog's not stupid. It makes the loudest noise it can. And it's evolved, it and the plant have co-evolved to kind of optimize the sound generation of the frog and the plant. And that's a published in Nature paper.
about phasing stuff, because it does appear with various...
Well, there's the famous firefly synchronization and other things like that. It's not clear that that helps the firefly at all. It's just an accidental effect of oscillator synchronization. Could be. Or maybe, you know, a tree that's all blinking on together is more attractive or something. Hard to say. birds certainly, you know, talk. They certainly synchronize the way they twitter at each other and so on. So I don't know. Yeah.
I was wondering if there's any obvious correlation between the number pi and sound. Do those two worlds cross over in any obvious way?
Well, there's a. I wouldn't use the word correlation because that implies statistics, and you know that's not what we're after here. But pi is such a ridiculously general concept that it's correlated in some sense with everything. Everything that's got anything circular in it or sinusoidal in it has got pi buried in there somewhere. So whether you consider that to be a profound or a trivial fact is a matter of taste, really. Well, thanks for listening. I would like to say that I do work at this university, and I have never been in this building before. So if you would like to come to my building sometime, you are hereby all invited, and I'm happy to talk to anybody about anything, anytime. Thank you.
Art side, you want to talk about art side?
Oh yeah, we did. The first event in this series was a thing that I organized at the Fields Institute. We meshed it with a thing I organized at the Fields Institute called the Art Science Salon. And if you weren't there, you know, send me an email and I'll put you on the mailing list for future salons. We put together artists, not always musicians, and scientists, not always physicists, and we kind of mashed them up using the Fields Institute as our venue. It's usually an evening event, and then we all go to the pub afterwards. So it's called a salon.
And the lectures from yesterday will be on your website.
That's correct. They're on the Fields Institute website. It was those lectures were all recorded as part of our Salon series. So if you look on the Fields Institute website, you can watch yesterday's lectures after a week or so when they get them ready to put them up.
What about the recording of today's lecture?
I have no idea about that.
Well,
There's a camera.
That has to be determined. They will be
They'll be available
somewhere
at some point.
at some point.
Out there. Okay, thank you.